The other subsystem we talked about or we listed was the fourth time I am making that spelling mistake, I think. So, now I mean you think about it for a second, right? You say, okay, I have this, I have a battery. So, I have battery plus and battery minus. Now, I am going to put something in the middle. What that something is, I do not know. I am just giving it a name called power management unit or power management subsystem, and this is now going to deliver power. What the microcontroller told me was, said, please give me 1.2 volts, because 1.2 volts is what I am designed for. So, this power management unit magically generates 1.2 volt. This is what I am supplying to the MCU, and for the purposes of this conversation, we are going to model that MCU as a current source, right. Let us say that MCU, for example, takes 100 milliamps of current, right. So, now it is interesting to say, okay, 1.2 volt has to deliver 100 milliamps of current. Now, does this mean that this 100 milliamps of current has to come from the battery, or will the amount of current coming from the battery be lesser? It is an important question to answer, because now it is actually, if you look at the power that it is taking is what is that? It is 120 milliwatt. That is the power it is taking. Now, if I end up taking this current from the battery, right. So, let us say case 1, right. Case 1 is where the current drawn from the battery is also 100 milliamp. We will come to what this black box will look like for that to happen, but let us say current drawn from the battery is also 100 milliamp, then the power drawn from the battery will be equal to 100 milliamp into the battery voltage. Power is V times I, right. Power needed by the MCU is, so this is our MCU, okay, is actually 100 milliamp into 1.2 volt, which is 120 milliwatt. Now, VBAT, when the battery is fully charged, if you use a lithium polymer battery, could be 4.2 volt. So, let us, for ease of numbers, assume that when I did this measurement, VBAT was 3.6 volt, right. So, when VBAT is 3.6 volt, this will be 360 milliwatt if VBAT equal to 3.6 volt, right. So, now if I were to look at this efficiency and say efficiency equals power needed by power drawn. This is 120 milliamp by 360 or 120 360 milliwatt, which is 33%, right. So, if you say, okay, I do not want to be building complex power management subsystems and all that, that system needs some current. I know it has to, it will only operate at a certain voltage. So, can I put some simple regulation or a regulator circuit that only takes care of the voltage difference. Current, there is nothing happening. I am just going to supply that same current from the battery, but I have a mechanism to take care of the voltage difference. What you would be doing in that case is trading off simplicity for efficiency, right. And that is what this calculation sort of shows, that let us say the current drawn by the microcontroller has to be completely serviced by the battery without any attenuation or any without any attenuation, then the efficiency now is just going to be a ratio of the voltage at which the microcontroller operates to the battery voltage, and microcontrollers are typically designed in advanced technologies. So, supply voltage might be 1.2 or even lower, which means that the amount of efficiency you will get if the same current is drawn from the battery is very low. Now, there are cases where this is okay to do. Now, for example, if I say so let's keep this in mind, okay. So, this is one calculation. Now, let us say same case, this is my PMU, I have the battery. Now, instead of driving the MCU, it is driving the RF. Okay, so, my connectivity system has an RF, and that RF connectivity system says that for me, because I have to put out quite a bit of output power, I need a large supply voltage. So, what I would really like is a 3.3 volt supply, right. Argument sake, let us say okay, it needs a 3.3 volt supply, or maybe let us say this battery we support up to 3 volts. So, this also says give me up to a 3 volt supply. Now, let us say this is 50 milliamps of current. Now, if we persist with case 1, what is case 1? Case 1 means I RF is equal to I battery, which means that whatever current the block wants is coming from the battery without any attenuation. In this case, the efficiency will be just VRF, whatever supply, or VDD, just let us say is VDD RF, which is the supply that maybe this RF block needs, divided by VBAT. So, if I keep persisting with that 3.6 volt, now this is 10 by 12, this is 83%. So, we were in the previous case we were at 33%, now we went to 83%. So, it is worth understanding that now if I am going to let the same current flow from the battery to service my block, the efficiency I will get is defined by the ratio of voltages. So, the voltage that my block needs divided by the voltage that the battery is at is the efficiency I get, right. So, this ratio will be high if the block requires a high voltage. So, if anyway it is producing high swing, if anyway it is going to take a high supply voltage, then at that point it might be okay to say my efficiency is looking pretty decent. Let me not complicate the level of thinking I have to do. I just have to come up with a simple system that will source the same amount of current without really doing anything while making sure that the voltage is regulated, right. So, a system of that sort is called a linear regulator. Again, this also we will spend more time on, but you can think of a linear regulator in the context of okay, whatever current the block needs, that current is coming without any reduction from the battery, right. And all that the linear regulator is doing is saying that somebody has to take on the voltage load. I am getting 3.6, I should give only 1.2, the rest of the 2.4 volt I will sustain. That is what that linear regulator block is doing. This is typically low efficiency, but simple design. It is also simple in terms of external components, etc. We will see that in a bit. The other option is to say that, see, you want, for example, let us say I go back here, right. You can argue now that you can say current drawn, current required by MCU is 100 milliamp. Now, my battery is at a much higher voltage. So, what if I keep my battery connected, and we are going to do this in English, okay, the implementation will look different, but let us try to understand it in English. Now, if if the output voltage that is needed is 1.2 volt and my battery is at 3.6 volt, it is effectively saying if I keep my battery on for 33% of the time, then I can service that current, right, because the amount of power it needs is 120 milliwatt. I have 3.6 volt. So, what I will do is 33% of the time I will make this 3.6 volt available. So, it will provide whatever current is needed, and that power it has to maintain somewhere, and then over time it will average out. Or in other words, let us say, oh, you are taking if I go to an energy calculation, I need 120 milliwatt of power all the time, right. That is my energy requirement on one side. The energy available on the other side is 360 milliwatt 33% of the time. So, now energy at the source matches energy at the output. So, energy that is needed is matching energy that is provided, which means that the system is starting to approach 100% efficiency. Again, I am trying to explain these things with English because benefit of English is you need no prerequisite. You do not need to understand how regulators work, you do not need to understand how that system is put together. All you need to get is oh, okay, you know, if I understand ratio of energy is efficiency, and if I find a path to be able to match energy at the source to energy required at the output, then I am getting close to 100% efficiency. That is all the understanding you need to grasp that. So, now the way that is done is through something called a switching regulator, but so let us just sort of finish this thread here. Current required by the MCU is 100 milliamp, which means power required is 120 milliwatt. So, energy required is 120 milliwatt into whatever time it is running for, right. Now, power available is 360 milliwatt because it is 3.6 volt into 100 milliamp. Energy available is 360 milliwatt into a factor that we will call duty cycle, right. Now, by playing with this duty cycle, I can get better and better efficiency. Efficiency is energy required by energy available, which is, this is duty cycle is a percentage, so it has to be multiplied by T. So, this is 120 milliwatt into T by 360 into T into duty cycle. So, T cancels. So, this is 1 by 3 into duty cycle, 3 times right. So, let us sort of mean. Right. So, now what you can do is you can say that okay, I was at 33% efficiency in the previous case. Now, by playing with this duty cycle, I can keep improving the efficiency, right. It is not possible to get more than 100% efficiency. So, if you make the duty cycle too small, it means that the energy available is less than the energy required. So, you will not be able to deliver to the microprocessor the current it wants. If you now ration the duty cycle to the point where you have 100% efficiency, then you are just able to deliver exactly the amount of power it wants, but invariably you will need to consume some power. So, what you will have to do is say that okay, let me play with this duty cycle to get maybe 90% efficiency, 95% efficiency in operation. So, that now is done through something called the notion of duty cycle itself means that indicates that something is switching, right. Duty cycle is usually is defined as the ratio of on time to time period, which means something is switching. So, these class of regulators are called switching regulators, where you get high efficiency, but design is complex, right. So, these are the two types of regulators you can think of. So, switching regulators can either be step down switching regulators, can also be step up switching regulators. We will look at some of this, but maybe not in too much detail. Again, as an embedded system engineer, it is important to understand, okay, how does the system operate, what does it mean for me as I put this system together. Maybe we will get to that in just a bit in terms of what the embedded engineer must care about, but let us sort of take this thread to its conclusion. So, a power management subsystem now, a PMU subsystem will have one or more linear regulators, and it will have one or more switching regulators. It operates from the battery, and it produces maybe an array of different supplies depending on the number of regulators you have. So, VDD 1, VDD 2, VDD 3, ground 1, ground. So, it can generate a range of different supply voltages based on the number of instances you have of the regulators themselves, right. So, this again is a completely analog subsystem. You might have digital logic, which is control logic, but very minimal digital, largely analog subsystem. I have not shown the external components here in the subsystems, we will come to that, but it is, like I said, worth appreciating. We have been talking about, you know, which are analog subsystems, which are mixed signal subsystems. This again is a 100% analog subsystem. Okay. So, that is the PMU or the power management. So, one of the things I'm hoping you will be able to appreciate with this is that, you know, we've really not relied on any prerequisite knowledge up to this point, or even if we've relied on very little, right. So, it is possible for us to in our head generate a functional view, a block diagram view of the system without really getting too limited by, oh, I need to know this to be able to do this, I need to, this background knowledge I need. For us to make a framework of this is how the system comes together really does not need too much of that knowledge. The knowledge is of course specialized, we will look at where it can be where it gets applied, but for a system engineer to develop a top level view of the system he is putting together, that specialized knowledge is really not a must, and putting that framework together is actually a good first step to understand, oh, where does the specialized knowledge needed and where can I rely on specialized knowledge that somebody else has and has actually put together in the form of a component that I can use, right. This again is a point I made a short while ago, maybe I am laboring some of these points, but I think worth laboring over. So, again 100% analog subsystem, this is the power management subsystem. I think we also had the LED subsystem, let us just for completeness sake finish that as well. So, with the LED subsystem, LED subsystems are actually even simpler. You have maybe the IOs for R, G and B. So, we will call them GPIO R, GPIO G, GPIO B. So, we have a red, green, blue LED, RGB LED, which is the three primary colors, and each of these LEDs is getting driven by a general purpose IO, what we are calling a GPIO, and these general purpose IOs reside on the microcontroller. So, there is some logic on the microcontroller that says okay, now go flash red. What that GPIO will do is have the digital signaling to be able to produce the effect. It just decides when and for how long which LED needs to be on. So, this then so you think of this as a switch. So, maybe this is coming from battery or this is coming from ground. So, let us also say, let us say it is coming from ground. So, basically you have, you can think of it this way, right, that the GPIO is essentially a switch connecting to ground. That GPIO is the control to this switch. Maybe I should what we will do is let us just move the text here. Let us go back here, let us put. So, let us say that these are switches to ground. Now, GPIO R might be this control, GPIO G might be is this control, and GPIO B might be is this control, right. So, now when GPIO R, or let us say I want red light to be on, this switch is going to go close and that the GPIO will take care of. It's super simple. Now you have to, the way this works is you have an LED that is maybe, so let us, sorry. So, you have the different LED lights here, and these lights need to be driven by from the supply now. So, the way LEDs glow is that you flow current into a diode, it will glow. So, the simplest way to generate a current is to have a supply and a resistor. It is not a perfect current source, and I think that again you might have covered in this class earlier. But for the purposes of visual indicators, it might be the simplest system to build. So, one option is to say, okay, so let us say this is battery plus, right. So, you have right. In its simplest form, this is all it is, where from the battery I have resistors, and now the turn on voltage of these different diodes is going to determine how much current flowing through the resistor. So, it is a function of both the turn on voltage of the diode as well as the battery's voltage, and that will dictate how much current flows through. Now, it is not a perfect current source. So, depending on how the battery voltage varies, the current through these resistors will vary, which means the intensity of the LED will vary. This is one implementation, or you can say no, this is not, this does not cut it for me. So, you can say, going back here, I operate from the battery and I have some current source generator that then connects to these three different LEDs. So, this is R, G, B. Now, you can say okay, I want whatever be the battery voltage, I want that light intensity to stay exactly the same. One way to achieve that is by ensuring that the current source is independent of the battery voltage. So, it is pretty close to an ideal current source, which means that it also needs to be generated to ensure that the amount of dependence on VBAT is very, very small. So, that is possible to again do depending on how much importance you place to these things. So, you could settle for a very simple implementation, or you could go with something more complex like this. But what is worth recognizing again is whatever you do is still a 100% analog subsystem. So, an LED subsystem is also a 100% analog subsystem. The only thing to bear in mind now is what are the turn on voltages of these LEDs, and how do the turn on voltages of these LEDs correspond with minimum battery condition, what IO strength I have, how does the voltage drop work, etc. Right. So, for example, if blue LED, right, blue LEDs typically have a turn on voltage of 2.1, 2.2 volt. So, if you are using only let us say I have to generate a current source. Now, if your lowest battery can go to 3 volt, the amount of voltage headroom that you have to generate the transistor is very small. Or if you go back to maybe a simpler use cases, let us say we just focus on the blue LED for a second. So, let us say I have battery voltage, I have some resistor, and this is driving, this is my LED. So, this is the blue LED. So, this voltage when the LED is on, I can roughly assume is 2.1 volt. VBAT can go from 3 to 4.2 volt, and let us say this is 500 ohms, just taking some numbers, right. So, when VBAT equal to 4.2 volt, what you have is I through the resistor is 4.2 minus 2.1 by 500 milliamp, 500 ohm, which is 2.1 volt by 500 ohm, which is 4.2 milliamp. When VBAT is 3 volt, the current through that resistor will be 3 minus 2.1 volt by 500 ohms, which is 0.9 volt by 500 ohms, which is 1.8 milliamps. So, now if you go with a simple implementation like this, the challenge becomes that now between my maximum battery condition and minimum battery condition, the current has reduced by more than 50%, which means there will be a very visible change to the intensity based on the battery voltage. Now, you can say, you know, that is the thing with engineering, right. It is not like oh, you should do only this or only that. These are options in front of the engineer. The engineer can say, yeah, it is okay, you know, I am worried about how much this is going to add to the cost of my product. So, I am going to keep the solution simple. I am willing to accept the 50% or more than 50% loss in intensity when the battery voltage drops. Or you can say, no, I am very particular that the intensity be exactly the same. So, what I am going to do is I am going to generate that current source, which will even in that 3 volt condition or low battery voltage condition will continue to deliver that 4.2 milliamp. So, the user perceives no change in intensity. Now, these are design decisions, and it sort of leads into what into the point I want to make next, right. But before that, before we get there, let us just quickly recap the LED subsystem. It is a 100% analog subsystem. There are multiple ways to implement this analog subsystem. What is worth recognizing is that the control is one way. It is the MCU which decides pretty much when what light needs to come on and for how long. All that the LED subsystem is doing is ensuring that a current flows into the diode. That current, if you can either say I want to keep implementation simple. Now, this is an engineer's, this is the system engineer's choice. I am going to keep the implementation simple. I accept the trade off with respect to the intensity, or no, I can't accept the trade off with respect to intensity. I am going to keep the system complex, right. That is an engineer call, complex in the sense there will be more cost. So,